Hi there, and welcome to day 2 of the quantum field theory course as part of this summer school. It's the third lecture. Today's topic is going to be on the Klein-Gordon equation. So we're mostly going to be considering the classical theory of the Klein-Gordon equation in this lecture, and then later on we'll move on and quantize it. So I wanted to start by recapping some of the important results. So just to remind you, we said that we can get the equations of motion, or the field equations, which is what the Klein-Gordon equation is, from a Lagrangian. Okay, so the Lagrangian that leads to the Klein-Gordon equation is a Lagrangian for a real scalar field. So actually, you can get a Klein-Gordon equation for a complex scalar field as well, but we are limiting ourselves to this simple case where we have a field, function of space and time, and it's real. And in that case, and it's a real scalar field, the Lagrangian, or more technically it's the Lagrange density, but I'll often just say the Lagrangian, is the derivatives of the field minus a half m squared phi squared. And so we said we can get the field equations, or dynamics, from the Euler-Lagrange equations. So you should be able to go from this Lagrangian, and using this Euler-Lagrange equation, you can derive, or you can end up with the Klein-Gordon equation. So the Klein-Gordon equation pops out at the end, once you use this machinery, is the following equation. So it's d mu phi plus m squared phi equal to 0. So we showed that how that worked in detail yesterday. That's using this Lagrangian formalism. Let me just also briefly remind you of the Hamiltonian formalism. So in the Hamiltonian formalism, we introduced a new field. So we introduced a new field of space and time. It's called the conjugate momentum, or conjugate momentum density, and this can be calculated if you know the Lagrangian. It's simply dl by dot. So it's the derivative of L, curly L, with respect to the time derivative of the field. And we said that this is quite similar to what happens in classical mechanics. The conjugate momentum is dl dq. Now there is an important difference here. Okay, so this conjugate momentum that we get is a field. It's not a number. So, normally when you think about the momentum associated with some field, you might think about, a number. So, and it might have 3 components, px, py, pz. But this is not the momentum that gives you a number, right? This is a new field. So if you wanted to get the momentum, well, I also told you how to do that yesterday. So you can get the momentum from the energy momentum tensor. Okay, so this procedure, if you calculate the energy momentum tensor and integrate it, this really does give you a number. So this is the physical momentum, if you like. This pi is a field, but it has the name conjugate momentum. So once we introduce the conjugate momentum, it's then relatively straightforward to calculate the Hamiltonian density. It's pi times phi dot minus the Lagrange density. Okay, so for this theory above of the real scalar field, so for this Lagrangian, hopefully you've been able to calculate that the momentum, that the conjugate momentum ends up being phi dot, and Hamiltonian density ends up being a half I squared plus grad phi squared plus m squared phi squared. Okay, so those are things that you should be able to calculate. Okay, so that's just the recap, and then we'll next go on and think about solutions to the Klein-Gordon equation. Okay, so we've found our classical solution, our classical wave equation, which we now want to find a solution to. Okay, so we know that our field, our real scalar field, okay, is going to satisfy the Klein-Gordon equation. And so our first challenge is to find the solutions of this classical wave equation. So I want to go through two ways we can get solutions. So the first is to use an ansatz or a guess, okay? And since this is an equation describing a free real scalar field, well, we know, or you might have some intuition that the solutions for real particles, the particles that aren't in any particular potential, are plane wave solutions, okay? So we're going to guess an initial solution, and we're going to guess that the solution is a plane wave. So if you wouldn't have guessed this, let me just tell you that a plane wave solution is a good solution to the Schrodinger equation. It's going to turn out to be a solution to the Klein-Gordon equation. It's also a solution to the Dirac equation. It's a solution to all of these wave equations. Okay, so guessing a plane wave solution is a good place to start. So what is a plane wave solution? Well, let's write it down. So we need a function of x and t. Okay, and a plane wave solution is simply a exponential e to the I kx, and normally there's some amplitude function, so let's call the amplitude a. And I don't know about the sign per se, so let me allow the sign to be plus or minus. Now here, let me remind you, I'm using 4-vector notation here, so this k dot x is shorthand for k mu x mu. And here, where k mu is the wave vector, correctly, let me write down the index up. The wave vector has components omega in the time component and k in the spatial component. Okay, so then k dot x is simply omega t minus the 3-vector dot product k, the vector k dotted into the vector x. This is a shorthand way of writing omega t minus dot x. Hopefully I won't make mistakes, so hopefully it'll always be the case that if I'm talking about 3 vectors, I'll have the line underneath, and if I'm doing the shorthand of the dot product, I will not put the line. So how do we show if this is a solution? Oh, maybe one other thing I should do. Let me put a plus and minus on the phi's here, okay, to tell me about what sign in the exponent I have, okay? So this ansatz is going to be a solution to this wave equation if it satisfies the wave equation. So let's put it in, let's substitute it in and check to see if it is a solution. So to substitute it in, we need to differentiate the field. Let's go ahead and do that. So we have an exponential here. Exponentials are the easiest functions to differentiate. We differentiate this exponential with respect to the space-time derivative. We simply pull down a factor of plus or minus ik mu, so that index mu, and we get the exponential back. Okay, so if we differentiate twice, which is what we have to do because it's the double derivative that enters into the Klein-Gordon equation, we simply pull down 2 factors of k, so one with an index up, one with an index down, as follows, and we keep the exponential, so it's a e to the plus or minus ik dot x. Okay, so we can simplify this a little bit. If we square plus I, we get minus 1, and if we square minus I, we get minus 1. So we always get a minus a mu e to the plus or minus k dot x. Okay, that's what the derivative is. So our ansatz, our guess, the solution, if minus k mu, I'm just substituting into the full Klein-Gordon equation. So we've got the derivative piece that we calculated. We also need to write down m squared piece as well. So plus m squared in our expression for phi. This is set equal to 0. Okay. So what do we have here? Well, we have minus k mu plus m squared we've got the a, and we've got our exponential term must be equal to 0. So in general, this will be a solution if the Klein-Gordon equation, if the thing on the left-hand side is equal to 0, and the way that we can force this to be equal to 0 is obviously to put this term in brackets equal to 0. So it's a solution if k mu equals m squared, or remembering what k mu is. K mu is going to be omega squared minus k squared. It's a solution if omega squared k squared. So it's really k dot k. That's what I mean by k squared. Or sometimes you'll see it written as the absolute magnitude squared. So it's k squared plus m squared. Of course, you'll recognize this as simply the dispersion relation that you normally get in special relativity for a particle of mass m. Okay. Compare it to that. We're using natural units here, obviously, so we don't have the c and h bar factors. We've set them equal to 1, but we can identify the frequency is like the energy, and the wave vector is like the momentum. My arrow under the momentum because it's a vector. Okay, so we've shown that that this can be a solution. This plane wave that we had above can be a solution, and both the plus and minus terms in the exponent can be solutions, so long as our k, as long as the k that enters our guess satisfies this relation, or equivalently write it in the 4-vector notation. Okay. So our general solution then for a given value of k, specify what a k is, okay, is going to be phi as a function of x and t, is going to be, well, we saw that both the positive and the negative terms in the exponent were solutions. So we might think that this is going to be the solution then. Okay, so it's a linear combination of both of the terms we had above, where we had the minus in the exponent and the positive in the exponent, and we need to specify that omega squared is k squared plus m squared. Okay, so this isn't quite correct because there's one extra condition, that one extra thing we know about phi that we haven't ensured holds for this solution. Okay, the one extra thing that we know about phi is that it's a real scalar field. So we need to ensure that the solution that we've written down here is actually a real field. Okay? So one way of testing if something is real is to ensure that phi is equal to the complex conjugate of phi. Okay. So we can easily check that here. So we require that a e to the I dot x. We have the second term. So if we take the complex conjugate, we'll get a star e to the plus I k dot x plus b star the minus I k dot x. Okay. And so we can see we can see that this will be real if our term e to the plus ikx is the same. So we need to ensure that this coefficient a star equals b, or alternatively that a is equal to b star. Okay. It's real. To be real, we require a star B. Or obviously then A equals B star. Okay, we get this same conditions. So our real solution then is phi function of x and t. Okay, is what we had above. So a e to the minus I k dot x. And now we have, we know what b should be. B should be A star. Okay, and then this ensures that our solution really is a real solution. Okay, and again, I'll state it. This holds if omega squared is k squared plus m squared, okay? And for any value of k. We don't have a constraint on k, okay? So k is still a free parameter. We know that once we specify k, and if we know what this m mass parameter will be, then we can calculate what omega is. But this is a solution for value of k. So we can actually write down a more general solution by ensuring that we sum over all possible values of k as well. Okay. So if k is a discrete parameter, we wanted to sum over it, we would have, well, we would just sum over it. We would sum over the, well, it's a vector, so there's really three components there, right? There's x, y, and z components. So our full solution, if it were discrete, well, we can now label our coefficients with a k subscript. It's like that for each value of k, as long as the second term is A star, if the first term is A, we'll have a solution. Our solution, as I said, needs to have an A star here. Okay, so this would be the general solution if k was discrete. Of course, k isn't discrete. It can take continuous values. So instead of doing a summation, we should really do an integral here. We're going to integrate over all the values of k. I'm going to write that as d3k. Okay, sum over all possible values of k. Now there's a choice you can make here as to how you parameterize your coefficients. So there's various conventions in use in the literature. Let me tell you the convention that I'm going to use for my solutions. So I'm going to write let's measure this d3k bit as d3k over 2 pi cubed and 1 over root 2 omega k. In a sense, what I'm doing here is I'm just redefining these k terms. So I'll put a tilde on it in this equation. Okay, so what I've done, compared to the line above, let me bracket in the right place. There it is. So compared to the equation above, I just have a different version of the a here. So I've got an a tilde. I factored out this factor of 1 over root 2 omega k. And because I'm taking the square root, then my omega k I'm going to define to be the positive square root of k squared plus m squared. And I've also got this value 2 pi cubed. So we'll see this later. The reason we do this is so that we have a Lorentz invariant integration measure. There's also different conventions in use, as I've said. So in the notes, the typed notes that accompany this course, there's a factor of 1 over 2 omega k here instead of 1 over the square root of 2 omega k. So I'm putting in the square root because I follow the convention of Peskin and Schroeder. Peskin and Schroeder use the square roots, but I'm sure in your career so far you've realized that in particle physics there's many conventions in use, and unfortunately not everyone uses the same convention. So here's another example of a convention. So this is the convention that I will use throughout the lecture note. Okay, so here then, just to summarize, this is our classical solution of the Klein-Gordon equation. We've found it by starting with this plane wave ansatz. We've shown that it's a sum of plane waves, one with an e to the positive ik and one with an e to the negative ik. And the other thing we had to ensure was that our solution was a real equation. Okay, so we do that by ensuring that these coefficients are the complex conjugates of each other. I said I would discuss two ways to solve the Klein-Gordon equation. So we've gone through the first method, which is this ansatz method, assuming it's a plane wave, substituting it in, ensuring that it was a solution. The second method I want to discuss is to use Fourier transforms. Okay, so let me remind you or tell you my conventions I'm using for Fourier transforms. So the Fourier transform of the field, we can decompose it into Fourier modes labeled K, T e to the I k dot x. Okay, so notice here we're integrating over the three components of x. So on my exponent here, I have e to the plus I 3 vector k dotted into 3 vector dot x. I'm using a convention where I put the 2 pi cubed factor all on the integral with the k. So this means my inverse transform, to go back the other way, my inverse transform is simply d3x integrate over phi x and t, and it's e to the minus I k dot x. Again, there's different conventions around. Some people will put a 2 pi r 3 over 2, and then they would end up with a 2 pi to the 3 over 2 in this integral. So I'm not doing that. All of my pi's go in this integral over k. Okay, so let's show how we can use this Fourier transform method to solve the Klein-Gordon equation, and let's see if we learn anything new by using this method. Okay, so we know that our solution, any solution, must satisfy this Klein-Gordon equation. To remind you, these are for the field with x and t, so it should be an x and t here as well. Okay, and we're going to find it useful to use the form where we break up space and time pieces. I'm writing the d mu here as dt squared minus the spatial derivative squared acting on my field. Okay, and the reason I want to do that is because in this Fourier transform, the way I've written it here, the exponent only contains the x, it only contains the spatial coordinates, not the time coordinates. So we can substitute in then our Fourier decomposition. Let's go ahead and do that into this equation. So substitute into our Klein-Gordon equation. So we get, well, we're going to have this d3k. Okay, so d3k, my k is not a function of time. It's going to sit at the front. And then I'm going to have this dt squared minus spatial derivative squared plus m squared. I'm going to have this acting on kt e to the I k dot x pieces. This should equal to 0. Okay, so I've just substituted in this form of phi xt into my equation. Okay, so we can manipulate this, or we can certainly take the derivative with respect to x on this e to the ikx. So the derivatives, this spatial derivative is not going to act on this function phi k and t. It's not a function of x. It's only going to act on the exponent. We're going to have, all right, let's write down the d3k piece. So we're going to have dt squared, and it will act on the bits that have time dependence. It's okay, so this function, this kt function does have time dependence. And then this, as I said, this spatial derivative is going to act on the exponential, and it's going to pull down factors of ik. Going to pull down 2 factors of ik. And we'll get the field. So it doesn't differentiate the fields. Let's write the field, and I'm going to leave the exponential. I'm going to pull it out side in it at the end. Plus m squared phi e. As I said, I need to remember to write down the exponential, and this should be equal to 0. Again, we have the only way that this can be equal to 0 in general is if this term in the square, or not square brackets, in the curly brackets, all of this stuff is going to be set equal to 0. This is a solution if dt squared, so the time derivative acting on the Fourier modes, which are labeled by k, is equal. Let's look at this. So we get an ik times an ik. So we get a minus a squared here. So we'll get a plus k squared overall. I'm going to bring it across to the other side. So we get a minus a squared plus m squared times the function. Okay, and I'm going to write this as minus omega squared phi. So I'm introducing omega squared, which is equal to a squared plus m squared. So this is an equation which you will have met before. So this equation is simply the equation of a simple harmonic oscillator. What we find each Fourier mode of this real scalar field satisfies this equation that we met in the classical mechanics section, the simple harmonic oscillator equation. That's nice because this is a nice simple equation that we've been dealing with for years and years and years, possibly even when you were at school. And so we know what the solution of this equation is, right? So the solution of the equation above of this equation is simply that phi t is phi k with at some reference time, let's choose t equals 0, times an exponential. So in general, you'll have e to the plus or minus I omega t. So we can substitute this solution then for phi of kt back into our Fourier decomposition. Okay, so we can substitute in phi k and t in here. We now know what it is. Find phi xt then. It's integral over d3k 2 pi cubed. Let's substitute in for phi of k and t. So we know what the time dependence is. It's an e to the minus omega t. And I'm going to choose the minus I omega t factor. And we have to remember about the e to the ikx factor was in, let's go back up, that was in our original solution. We had the d3k over 2 pi cubed, the e to the ikx, and we substituted in the new piece that we found. Okay, so what is this? Well, this is some time independent constant which is labeled by k. Before we simply labeled this constant as a. Let's do that again. So we have some constant term which depends on k, but it's constant with respect to time. Okay, so we'll label it k. So this is now labeled a k. And we have this exponent, or these two exponents, which we can now write as e to the minus I k dot x, because remember k dot x is omega t minus k dot x. Again, we have to ensure that our field is actually a real solution. One way we can, at the minute, this is going to be in general some complex solution. So remember, have complex numbers x plus iy. If you do z plus the complex conjugate of z, you're going to end up with a real number. So the easiest way to ensure we get a real version, let me see, general complex, the easiest way to get a real function is simply to add the function to its complex conjugate. So that's the solution which is real then is going to be d3k 2 pi cubed. So this is a real piece, and we can just add function and do the dot. You can add the function to the complex conjugate. And again, we've ended up with this Fourier decomposition mode with a similar form that we found before. So there was, again, slight difference. So one thing that we're going to choose to do, put in this normalization factor 1 over the square root of 2 omega k. So as I said, you can think of this as factoring out of the a terms. So with both the ansatz method and with this Fourier method, we've ended up with the same solution. The additional thing that we learned with the Fourier method is that each Fourier mode satisfies the simple harmonic equation. Put it here. Each k component of this field satisfies a simple harmonic equation, and that's good because a simple harmonic oscillator is something that we know how to solve. Okay, so I just wanted to pause for a couple of minutes just to give a little mini summary of what we've done so far. Okay, so we've started with Le Lagrangian with a theory of a real scalar field, and we can also work out what the Hamiltonian is for this theory. Okay. So using the Euler-Lagrange equations, we can work out what the field equation is from this Lagrangian. It's the Klein-Gordon equation. And now we've looked at how we can solve the Klein-Gordon equation. We found the solutions. So we've shown that the classical solutions are a superposition of essentially plane waves, so e to the ikx and e to the minus ikx solutions, where we sum over all of the possible values of k. And we had to ensure it's real by making sure that our coefficients were the complex conjugates of each other. And there was one extra condition we had to find to make sure this was a real solution, and that is that omega k satisfies this equation. So it's related to the k factors that we're integrating over. Okay, so that's our solution. Now, one thing that we learned, and which we're going to use, important fact that we're going to use, is that in momentum space, so when we Fourier decompose this solution, each of our Fourier modes, so the phi k t functions, they satisfy the simple harmonic oscillator equation. It's a nice simple equation that we've studied many times in physics before. Again, the omega squared term here is simply related to k squared plus m squared. So what we find is that our solutions to this Klein-Gordon equation are simply linear superpositions of an infinite number, infinite because k has an infinite number of values, but it's an infinite number of uncoupled, so this is an uncoupled oscillator equation, but it's uncoupled simple harmonic oscillators. One harmonic oscillator for each mode k. This is going to turn out to be useful when we want to quantize this theory. So everything we've done so far is just looked at the classical Klein-Gordon equation, but we want to quantize it. So one thing we can do then, and one thing we will do, is to quantize this theory using techniques from the quantum theory of the simple harmonic oscillator, because we know how to quantize the simple harmonic oscillator. That's actually what we're going to discuss next. So if we can quantize the simple harmonic oscillator, hopefully we'll be able to take those techniques across and then also quantize this theory of the real scalar field. So that's where we're going next. We're going to look at the quantum simple harmonic oscillator and review some of the techniques that we can pull across to our field theory calculation. For the rest of this lecture then, I want to recap the techniques for quantizing a single quantum harmonic oscillator. So remember, we met the Hamiltonian for a single harmonic oscillator when we looked at the classical mechanics section. We find that the Hamiltonian was, it's h, it's a function of p, momentum and the coordinate x, so it's p squared over 2m plus a half, and I'm going to write it as m omega squared x squared. So previously we used the spring constant k. Here k is going to be related to m omega squared. That's the classical Hamiltonian. We want to quantize it. We're going to quantize it using this canonical approach quantization. Tells us this canonical approach to quantization tells us how to go from the classical Hamiltonian to the quantum theory. So the canonical approach is that we promote our Hamiltonian, our momentum, and our position to operators, rather than having just h, p, and x. So we now have operators, and the important thing about these operators, they obey, we're going to force them to obey commutation relations. Classically, they don't obey commutation relations. Although in classical physics, there are objects called Poisson brackets, and Poisson brackets are linked to commutation relations, but we're not going to get into Poisson brackets in this course. They do have commutation relations, so let me remind you what they are. So for the operators related to position, the operators associated to 3 spatial dimensions, so let me call it x1, 2, and 3, these commute with each other, and the operators associated with momentum, they will also commute with each other. So again, there's 3, px, py, pz, or p1, 2, 3. But the important point is that the the commutators with momentum and position, this commutator is not 0. So in a normal quantum mechanics course, you would say it's I h bar delta ij. 1 if I and j is equal to j, and then 0 if I is not equal to j. Now remember, we're using natural units, so I'm going to set h bar equal to 1. So I'm going to delete my h bar factor, or rather set it equal to 1 in this expression for the commutators. Okay, so in canonical quantization, we do this promotion of the Hamiltonian, the position, and the momentum up into operators. We impose these commutation relations, and then in the Schrödinger picture, you are probably most familiar with, these operators act on some states. Let me use bracket notation. Get a ket psi, function of time, and the time dependence of this ket evolves according to the following equation. So we have the Hamiltonian, tells us about the time dependence. So Hamiltonian operator acting on this state equal to I, and we're using units where h bar is 1, so it's simply I time the partial derivative of the state with respect to time. So that's kind of this bit's kind of the general, what happens in generally going from the classical theory to the quantum theory. Let's turn our attention back to the simple harmonic oscillator. Consider how we solve this simple harmonic oscillator problem. So our Hamiltonian, in this case, we're going to promote it up to some operator, so we can do that. We can indicate that we've done that by putting these little hats on top. H is p squared over 2m. I'm going to use addition a half m omega squared x squared. Okay, so now in principle, there's different ways you can solve this problem. One way is to simply solve the Schrödinger equation. So as in other words, you go into the position space representation, you end up with a differential equation that you can solve for the wave functions, and you'll find the energies that way. That is a completely valid approach, and will give you the energies and tell you what the states in this theory. But it's not the most useful way for a quantum field theory course. So for a QFT, we're going to find another approach which uses ladder operators, or sometimes they're called correlation and annihilation operators. But we're going to find that this ladder operator approach is going to be more useful for what comes in lectures. Okay, so let's discuss this ladder operator approach then. So let me begin first of all by rewriting the Hamiltonian a slightly different way. So I'm going to factor out a factor of omega over 2 from my Hamiltonian above. Do that, I get x squared plus p squared over m omega. Now we have a Hamiltonian which is quadratic in x and in p here. So one way that you might want to proceed is to try and write this, well, try and factorize it into two terms that are linear in x and p. So we can, in particular, you might think about completing the square. Okay, so in other words, we could guess that our Hamiltonian can be factorized in a way where we complete the square. So in other words, we would have m omega x. So here are factors. Here we have factors that are just linear in x and p. And in the classical theory, quickly see that this would give you, this is another way of writing the Hamiltonian above, but we're not in the classical theory. We have to be a little bit more careful because of these commutation relations. So let's just double check to see if this guess for the Hamiltonian is the same as the Hamiltonian above. So we can do that by just multiplying out the expression. So we will get m omega x squared, and we will get p squared over m omega. And then on these cross terms, we'll get, well, let's see, we'll get I times x p, multiplying this term with this one, and we'll get minus I p x. And we know that p and x obey this commutation relation, so the order matters. In fact, I can rewrite this. Let me rewrite it as the commutator. IXP, that term. Okay, so here we're using the 1D problem. We can go back up and look at the commutation relation. So we find that x commutator of x and p in one dimension, so when I will equal j, will give me a factor of I. Get a factor of I commutator, I'll have I times I, I'll get a factor of -1. So I find that this guess isn't quite correct. It's not quite correct because of this commutator, but I can see then how I could factorize the Hamiltonian in the correct way. So let me we write down what the correct answer is. So the true Hamiltonian then is going to be this guess that we have, and then we need to fix the fact that we have this minus 1. Minus 1 is multiplying omega over 2. So if I add on omega over 2, I'll get the correct Hamiltonian. Okay. So it's conventional then to give a name to these products, linear combination of x and p. Okay, so normal to define operator A to be, well, it's almost what we have above, so let's write down what we have above. So A has the plus I p m omega piece, but it tends to be defined with an extra factor of 1 over root 2, and then A dagger, so the Hermitian conjugate, m omega x. So x and p are Hermitian operators, so they will be the same. Right, p dagger is the same as p, so I don't need to write p dagger, but I get a minus sign in front of the I. So you could quickly think, why do we do this? So are these operators observable, for instance? And the answer is, of course, they're not observable. They're not related to observable quantities because they're not Hermitian operators. We see that here. A dagger not equal A, so they don't give real eigenvalues. They're not associated with real observables. But we'll see second why they're still useful operators to define. Okay, so in terms of this Hamiltonian then, which can be written in terms of this guess that we have above, you can show very easily that the Hamiltonian, because I added in these extra factors of 1 over root 2, Hamiltonian can be expressed as A dagger A, and the little hats to remind you that they're operators, plus, I need to add on this omega over 2, plus a half. I pulled the omega right to the front of the expression. So both A and A dagger depend on x and on p. So we know x and p satisfy certain commutation relations, and it's also possible to show, I'm not going to do it in these videos, but it is possible to show that A and A dagger satisfy commutation relations as well. So A with A dagger gives 1. The Hamiltonian with A gives minus omega p. The Hamiltonian with A dagger plus omega dagger. Okay. In particular, this bottom one means that H dagger minus A H is equal to omega A dagger. Let's show where we can use this result. Okay, so if we imagine that there's a state n, which is an eigenstate of my Hamiltonian. Okay, so in other words, if it satisfies that when I act on the Hamiltonian on this state, I get back some energy that I'm going to label with n. Okay. We can then consider what happens if we act on the Hamiltonian, not on the state n, on the state A dagger n. Okay, so using this relation above, this commutation relation, we can write H A dagger as A dagger H plus omega A dagger. Using this result above, I can write H A dagger as omega A plus A dagger H. Let me act on the state n again. So why do we want to do this? So now we've swapped the order of the A and the H, so now I can act with H on n. I know what that gives. By definition, it's giving me back En. So I get En, that's a number. I get plus omega, which is a number, and I can pull out the operator left. In other words, what this is showing is that the state A dagger n is also an eigenstate for this system, and the eigenvalue is En plus omega. This is a new state which has a higher energy, and it's higher by an amount which is equal to a quanta of omega. So in other words, what's happening here is that this A dagger acting on n is creating some new state for me, which I'm going to label as n plus 1. So it's a state which has a discrete amount of quantum more omega. Okay, and you can go through exactly the same argument with A instead of with A dagger. So if you do the same argument with A acting on n, you would find that you get En minus omega. Tells us is that this A operator then acting on n lowers, I can label it by the state n minus 1. So I'm using the proportionality symbols here because there'll be some coefficient that you can define here depending on how you want to normalize your states. What's happening? Repeat, A dagger increases the energy by an amount omega, and A decreases the energy by an amount omega. Okay, now it turns out there's a special state in the theory, which is the ground state. We can define the ground state in terms of these operators, these A operators. Ground state is a special state that satisfies the condition that A acting on my state, the ground state, so I'll label the ground state with 0, the ket 0. This is going to give 0. So when I act on A on 0, I get nothing. And that's because the ground state is already the lowest energy state, so I can't have anything that's lower than the lowest energy state. So I can figure out what the energy of this ground state is using what I know about the Hamiltonian. So we've rewritten the Hamiltonian above in terms of A dagger and A. Write that down here. So it's omega A dagger A plus a half 0. And because by definition A 0 is 0, this first term when it acts on this vacuum state is going to give 0. And I'm simply left with omega over 2 on 0. So there's this finite energy associated with the ground state, the so-called ground state energy, which is omega over 2, or 0-point energy. So we can't have any states that have a lower energy than the ground state. But the nice thing about these A's and these A daggers is that they allow us to construct any states that we want. Okay, so by acting with A and A dagger, we can create a tower of states. So if I have ground state, I can go up to the next available state using A dagger. The next available state I would call 1. I can go up to the next state, another A dagger, give me 2, and so on. So I have this infinite tower of states and that I can find by using A dagger. And similarly, the operator A is the thing that brings me down this ladder of states. And I also then know what the energies of these states are going to be. So a general state n, while the lowest state is omega over 2. And as I use these ladder operators, well, I saw that acting with the ladder operators increases the energy by an amount omega. Every time I go up with A dagger, I get an extra factor of omega. In general, I'll get n omega plus the ground state, normally written as n plus a half times omega. As I said, in general, we can construct any state starting from the ground state. So let me write that mathematically. A state n can be constructed by acting on the ground state with this A dagger operator n times, and often you see this factor 1 over square root of the factorial of n, and we do that so that our states are normalized, so that the states n and m are normalized to a Kronecker delta. Okay, we've run out of time in this lecture, so let me just summarize the two key ideas that we've looked at. So the first is in the top box. So we've seen that solutions to the Klein-Gordon equation are linear superposition of an infinite number of uncoupled simple harmonic oscillators. Okay? And then the second thing we looked at is, since we know that Klein-Gordon has something to do with harmonic oscillators, we've looked at the methods for solving the quantum simple harmonic oscillator picture. And we've seen that a nice way of solving it involves what are called raising and lowering, or creation and annihilation operators, so these A and these A Dagger operators. Okay, so in the next lecture then we'll continue our story of how to go from the classical Klein-Gordon equation, use these creation and annihilation operators, find the quantized version of the Klein-Gordon theory.